Heat is something familiar to each of us. We feel the warmth of a campfire on a freezing winter night. Heat transfer is maintained by temperature differences. We will start with temperature and its molecular explanations in this chapter, and we will talk more about heat and heat transfer in the next chapter. The concept of temperature has evolved from the common concepts of cold and hot. However, human perceptions of what feels hot or cold is a relative one. Look at these three toilet seats. If you have a choice between them, which one do you prefer to use on a cold winter night? Can you rank the temperature of these three toilet seats? The answer is they all have the same temperature as the environment temperature. The scientific definition of temperature is less ambiguous than your senses of cold and hot. Temperature is operationally defined to be what we measure with a thermometer. To measure the temperature, we let the thermometer A to be in thermal equilibrium with the object B, and the reading in the thermometer A is the temperature of the thermometer A as well as the temperature of the object B. An important concept here is thermal equilibrium. If the object B is in thermal equilibrium with the third system called the object C, then the thermometer A should also be in thermal equilibrium with object C, so it will give our same temperature reading for C. This is called the zeroth law of thermodynamics. More accurately, the temperature of an object measures how much kinetic energy the object's molecules have. For example, hot object has high temperature and its molecules have a larger kinetic energy, while cold object has low temperature and its molecules have a smaller kinetic energy. Thermometers are used to measure temperature according to well-defined scales of measurement. The three most common temperature scales are the Fahrenheit, Celsius, and Kelvin. A temperature scale can be created by identifying two easy reproducible temperatures. The freezing and boiling temperature of water at standard atmospheric pressure are commonly used. The Celsius scale has the freezing point of water at 0 degrees Celsius and the boiling point at 100 degrees Celsius. Its unit is the degree Celsius. On the Fahrenheit scale, the freezing point of water is at 32 degrees Fahrenheit and the boiling point is at 212 degrees Fahrenheit. The unit of temperature on this scale is the degree Fahrenheit. You may notice that a temperature difference in 1 degree Celsius is greater than a temperature difference of 1 degree Fahrenheit. Only 100 degrees Celsius span the same range as 180 degrees Fahrenheit. The Kelvin scale is the temperature scale that is commonly used in science. Its lowest possible temperature is called absolute zero, which is related to the behavior of ideal gases, and we will talk about it in details later. The official temperature unit on this scale is Kelvin. Since the absolute zero equals to minus 273.15 degrees Celsius, we have the temperature in Kelvin equals to the temperature in Celsius plus 273.15. And it is important to remember that all temperatures must be converted into Kelvin before using them in an equation. Although we do have a temperature difference of 1 degree in Kelvin, it's the same as the temperature difference of 1 degree in Celsius. It is important to know how to convert between these three temperature scales. Let's look at this example together. In part A, to convert from Celsius to Fahrenheit, we use the equation temperature in Fahrenheit equals to 9/5 times temperature in Celsius plus 32, and we get 77 degree Fahrenheit. In part B, to convert from Celsius to Kelvin, we have the temperature in Kelvin equals to temperature in Celsius plus 273.15, and we get 298 Kelvin. There are many examples of thermal expansion. The expansion of alcohol in a thermometer, the expansion of hot air so that the hot air balloon rises, and the expansion of the railroad tracks and bridges. There are a few characteristics of thermal expansion. First, thermal expansion is clearly related to temperature change. Usually, the greater the temperature change, the more the expansion. Second, it depends on the material. For example, in a thermometer, the expansion of alcohol is much greater than the expansion of the glass containing it. Later, we will learn that an increase in temperature implies an increase in the kinetic energy of the individual atoms in the material. In a solid or liquid, since the atoms or molecules are closely packed together, this change in kinetic energy pushes neighboring atoms or molecules apart from each other and adds up a larger size of the whole body. For most substances, under ordinary conditions, there is no preferred direction, and an increase in temperature will increase the solid size by a certain fraction in each dimension. There are three types of thermal expansion: linear thermal expansion in 2 dimensions, and thermal expansion in 3 dimensions. Here is a list of coefficient of linear expansion alpha and the coefficient of volume expansion or 3-dimensional expansion beta at 20 degrees Celsius. If something needs space for thermal expansion but is prevented from doing that, it will experience thermal stress. Thermal stress can be really destructive, as shown in this picture. We will skip the calculations related to thermal expansion and thermal stress, and you may read the textbook for more information if you are interested.